Looks like pretty much everybody's put their answers in the chat right now. There seems to be a consensus on Mars and Pluto, but also some other interesting ones. But for now that we've kind of done some brief introductions over the chat, Mikey is going to tell us about an exciting opportunity to hear a guest speaker.
Yeah, on Monday at 6 p.m. as part of the engineering college's like Science Week, we have Nick Pudar talking, and you can sign up for that through a Zoom link. It's going to be on Zoom, and they have links to sign up for it on the Nebraska engineering page. It's right there at the bottom of the screen. John, do you want to paste that into the chat? But yeah, so this is, I think, a really good opportunity to hear from someone who's a professional in their field. But yeah.
I think some of the technology we're going to be using, he was part of developing it, right?
Yeah.
That sounds right. All right, then before we get started with the PDRs today, just a little bit of a word about how this is going to work. Each team is going to get approximately 15 minutes for presentation and questions. So we're aiming for about 10 minutes for the presentation and then 5 minutes to ask questions and give feedback afterward. The order we're thinking right now is that the mech team will give its PDR first on the truss, then we'll go into the 3 Big Red Sat teams, and finally the Special Systems team and the AXP electrical teams will present. Without further ado, let's give it up for the mechanical team.
Okay, so the first presentation will be on the mechanical team's payload, and they are really in charge of like the structural designs for pretty much everybody and for the support system of the balloon itself. And so this presentation will really cover the 3 main things: the management, the mission, and the design. So the management covering who's doing what, when they're doing it, and how they're going to pay for it, or what they have already paid for it. The mission will be really what they plan on achieving, what they expect to achieve, and any problems they might run into and how they're going to solve those problems. And then the design would really be how they modeled out their truss and their different shelving systems beforehand, what they used to model them, why they chose to use those things, and how they plan on obtaining like the set item in the end, and how they plan on putting them together, and then the eventual testing process to make sure everything holds up, the balloon launch and coming back down. The members of this team, we have Nicholas Christensen, Michael Hackett, John Heltzer, Nicholas Mancuso, Casey Mumo, me, Alyssa Simpson, and Shazia Syed. John Heltzer is the team lead, and he will be presenting the next couple slides.
Yep, thanks, Alyssa. Here you can see our schedule. We started back around Christmas ordering parts so that we would have them all in by the time our spring semester started. After we got our parts, we began modeling plastic components and using SolidWorks. And then we recently started to assemble our truss now that we have all the parts printing. This red line is where we are right now. Since our truss just got welded together, our plan sometime in the next day to the next week is to start actually testing it, which we'll talk more about later. Then after we test it, we have time built in to redesign the truss, maybe test it again if necessary, then do an integration test with the whole team on March 28th, and finally launch on April 24th. Here's a budget that we have. We ordered enough parts to actually make 2 trusses at the same time so that we wouldn't have to reorder parts after the first round of testing. The most expensive components were probably the T-slot brackets and the wine coolers, just because there were like 48 brackets that we ordered and like I think 24 of the wine coolers. We also put in some money in the budget for welding costs, which we've already paid out half of for the first round of welding on our truss. In total, all the budget comes to a little bit less than $600. Now Nick Christensen will talk about the mission.
Thanks, John. The overall objective of the mechanical team is to produce a truss that can support 6 payloads on a high altitude balloon. These payloads are going to be designed by the members of the Big Red Sat team. And as the mechanical team, we want to be able to make sure that they are able to go up and come down with relative ease. We have a few expected results for our project. One of them is that it can retain the integrity throughout the flight so that our truss is able to hold its shape and not break or fracture throughout the flight through the ascent and descent. Another one of our expected results is that the payload will be recoverable after landing, because the main thing that we hope to do in the whole of this project is be able to foster creativity for experiments, and we want to make sure that those experiments are able to be conducted. So making sure that the payloads are recoverable is definitely an important part of this project for us. And the final expected result that we have is that the truss provides a thermal and structural protection for the payloads, because as we go up, the payloads will be exposed to many different elements. And as the mechanical team, we take it as our responsibility to make sure that they don't freeze and that they don't get lost in a rough ride or anything like that. We definitely take responsibility, and we have an expectation that these payloads will be thermally and structurally protected throughout the flight. And then the risks and requirements.
Maybe skip it.
And the risks and requirements for our project are laid out in the mechanical risk matrix. Our first one, which is up here on the top left, is that the weld joints could break off the aluminum bars in the center of the payload. As we can see, that is low probability but high consequence. And we have tried to mitigate that risk by using a rigorous testing regimen to determine the max load of our truss so that we do not overload it during the flight. Our second one is that the clamps that hold on to the styrofoam coolers might snap. That is a little more probable, but we are also designing stress tests to mitigate that risk during the flight. Our third risk is that the parachute might not properly function when it is ejected. That one is also along the same probability, although a little less in the consequence in the grand scheme of things, we believe. And we're going to mitigate that by utilizing many resources at drop testing. We're going to drop it from different heights and make sure that the parachute is able to open. So that way we can be sure that we're not throwing this thing out there blindly without having properly tested that the parachute is open and functional. Our fourth risk is that the payload itself might fall apart before it lands on the ground. And again, we're going to mitigate that with a lot of drop testing. We're going to test to try to make sure that the ride isn't too bumpy on the ascent. We're going to try to make sure that the ride isn't too bumpy on the descent. And we're going to just try to test as much as we can so we can get the best possible idea to keep these payloads safe and allow the students to do their experiments that they design. And our fifth one is at the top of the containers could come off. That is very low probability and very low consequence, because we've come up with a way to lower the risk of that happening by designing custom lids throughout SolidWorks and using adhesives to stick them onto our CAN satellites as well. And next, we're going to hand it over to Nick Mancuso, who's going to talk about design.
The truss components, the aluminum T-slot frame is welded into the aluminum centerpiece. And it just, we chose it because it's not expensive, and it has stable connections, are very easy to be made. And then we used plastic T-slot connectors that we 3D printed in order to slot in. And the reason that they're a separate print from the horseshoes is because that allows it to print easier with the cross-section like X design. That helps it slot into the aluminum frame. The plastic clamp, the actual horseshoe design that wraps around the foam is, we chose that because that was the simplest way we could get the foam piece to stay in place. And then the actual styrofoam payload holder, we chose the styrofoam like wine bottle holder because it's lightweight and the styrofoam retains heat better than metal or plastic. The aluminum centerpiece is the basic design. Obviously, it's welded to the aluminum frame. Just stable and a good base for the whole thing. And then the brackets are just there once again to add more stability to the aluminum frame connection with the T-slots and the base. For fabrication, there are the two main parts of welding the connections, which is very stable. And then 3D printing. So we chose to 3D print most of our pieces because it's cheaper and more efficient than buying parts like that.
So for the testing, there's two main things that we really need to make sure that the design holds up to. And that is the shock test, which is the very abrupt and powerful force that's going to be caused by the parachute opening up and very quickly decelerating the payloads. And to do that, we'll have the truss suspended upside down. Well, it's symmetrical, but we'll have it suspended upside down, and we're going to figure out about how much force is going to be put onto the truss based on the weight of the entire project. And we'll drop a weight from the truss on the balloon hookups to make sure it holds up to that force. And then the other one is the drop test to make sure that as the payload comes down with the parachute, that it can survive that velocity that the parachute is giving it. And so we already did the math to figure out about how high we need to drop it from to actually get to that speed. And we found it to be about 3 meters. And so we will load it up with wine coolers and weights to simulate having the payloads and drop it and make sure that it survives the tests.
Are there any questions for the mech team on their PDR?
So I have a question. When you talk about clamping onto the styrofoam, I'm assuming it's like most styrofoam where something could rip through it pretty easy. Is there any control to make sure that because you're just kind of going around the middle, you don't really have like straps top and bottom, any control to make sure that the styrofoam container doesn't rip out?
Yeah, that's actually something we thought about. One of our initial designs had that kind of bottom component where we had the horseshoes and we basically had like a bottom piece to that. The only problem was that takes like 55 hours to print one of them. So it wasn't really feasible for us to manufacture. What we're hoping to do is, well, obviously the testing will give us a lot of data on whether our current design works, but we're hoping that some kind of adhesive like glue or Loctite will help secure the payload to the clamps.
Do you think
go ahead, Karen.
I was gonna say, could you do something simple like just a wire that goes around it that you don't have to print, or I mean almost something better than a rubber band?
Yeah.
And I don't know, Derek, you have
a fabric net of some sort would be good too, maybe.
So they're all good ideas.
Yeah, because what you have as far as the design there, I'm just thinking if you will get condensation and then it will freeze and so on, and whether that could possibly cause some slippage out of that bracket you have there. It may not be much, don't get me wrong, it may not just like totally just slide out of it, but you may get some motion. So yes, but I'm thinking more so as opposed to just like on the site, grab some wire, loop it around as a part of this being your design. If there was any way to possibly have, I'm almost thinking like teeth, almost like cleats, you think of the bottom of some baseball shoes or something like that, golf shoes, but just something that when you clamp that bracket on there, that it grabs that styrofoam that way and provides some hold. But that would possibly require some extra work with the welding and aluminum. But yeah, that's a good point. I was thinking the same thing, Karen, just so you don't have that slippage up and down within that bracket. And also something I was going to ask that you also take into consideration, if you go back to any one of those images and you see the screw or the bolt protruding past the nut, what you want to do is possibly get a screw or a bolt that's almost the same length of the entire assembly, meaning that it shouldn't protrude much past the nut once the nut is on there and is tightened. You don't want anything to possibly, it goes through a violent ride. You don't want anything possibly to whip up and hit the balloon and possibly cause a puncture that way. So we do our best right before we normally, and you could duct tape it, put some tape over it, because that's the way we do it. But given that you're designing this, specifically to not have those screws or nuts that protrude too much past, the assembly there.
Yeah, that's also a good point. The model that we have right now with the nuts and bolts is just using 2-inch bolts for everything, just because that was what we could find on McMaster. But I do know that there are 1-inch bolts that we can get, like, for example, around the clamp right there. That would probably be a better option, like you say. And then as far as the slippage goes, I think the points that you all make about wires or some kind of bottom component are very valid. I also think, though, that the design we currently have is printed so that the clamps are just a little bit smaller than the diameter of the styrofoam. So our intention is to clamp it tight so that it, maybe compresses the styrofoam a little bit, has better grip that way.
Yeah, we want to take a little bit of advantage of the fact that the styrofoam isn't totally rigid. And so by making it a little bit smaller and like kind of forcing it together, but like not like wildly, of course, but just enough to let to compress the styrofoam in that area. We wanted to see if that would be enough to hold it in. But I think the idea of a wire or cloth mesh is definitely like a really, really good backup to have.
And adding cleats, like you said, would be good if you're pressing into it. It kind of sinks into the styrofoam.
The question that I have about that is that a risk for the styrofoam starting to tear if we had those cleats?
I mean, it's gonna be up to you guys when you guys make it, but when you make cleats, it doesn't necessarily have to be something that's like really piercing into it. It could just be kind of more of ridges that adds a little more friction to it. It could go anywhere from like maybe shark spikes that actually do puncture it a little bit to just more ridges that are more friction, or a little rougher surface. So I think it could go anywhere, but so maybe you guys can test and see in person. So test one, print one out, see what happens.
Right. If you do it, just looking at that, what you would put it horizontal to the length of the styrofoam cooler. So, because that's what you're trying to avoid, right? You're trying to avoid the cooler from going up or down within that clamp. So if, either you have something that points directly into it, as you clamp it, it punctures it, but it doesn't have to be deep, as Ryan is saying, which is true, or either just have just something that comes out horizontally that just kind of bites into it a little bit to avoid or to limit that motion up or down within the clamp there. But if it's already designed to be a little bit smaller and provide that almost, I guess, like a blood pressure sleeve, right? It squeezes it just enough, but nothing to, terribly deform it or whatever. You should be fine as well.
I think ultimately when you guys go and do like your drop test, like you're talking about, if you have problems with, whether it's maybe either the parachute deployment or you're dropping it, if you have problems of it sliding out or slipping, those are just good solutions or ideas. But if you do your testing and it doesn't seem to be a problem, then good. And always test you always want to test what you expect and then maybe test a little more too, FYI.
Right.
So
Because I was going to say you may want to take a marker or anything and just mark on the styrofoam cooler, just trace the line
mm,
of the bracket so that if it does shift, you would see that shift as opposed to trying to eyeball it or anything.
It's-
So I think
yeah,
my
that's-
recommendation probably wouldn't be like adding something that would go like into the styrofoam, but I would almost put something directly above and below what would I consider like the belt clamp, kind of like put a bunch of tape so that way it can't laterally move up and down. And I don't think that would actually affect the integrity of the styrofoam at that point.
No, it wouldn't. It wouldn't. But what I'm thinking, like, since you're designing this up front, because part of it is that you don't want to show up on the site and you just whip out the duct tape, right? And you just start slathering on duct tape or mummifying the thing in duct tape. I mean, it's the safest thing. Don't get me wrong. We do it all the time. But you're in a great place to where you're designing this out front and you're looking at all of these now. So, take those things into consideration. But the ideas that are being floated are great.
Yeah.
When you guys test, I would like to add that you might want to have a couple ideas on your rig that you test and try them all, at least multiple in the same test, and then you can see what works out best for you. The clamps you have there, those clamps, those C clamps are 3D. Are those the 3D printed parts?
Yeah, the clamp.
Everything except
then-
for the hexagon inside is or octagon is 3D printed.
Gotcha. Yeah, I say, yeah, definitely test multiple things. Try to think of what's simplest too. Don't try to over design because it's just going to make it more complicated. I probably be of the mindset of trying to put, like what Beth was recommending, trying to put something maybe like tying it off with like a net or tape or something that's lightweight. I'm not sure exactly what, but just something like that. And see how that compares to maybe the spike idea. And I think looking at your requirements here, your main concern is it just while it's in flight, not necessarily once it hits the ground, it has to stay within that, right? Is that correct? If it was broken when it hit the ground, obviously you don't want it flying pieces all over the place, but as long as you can recover all the pieces, if it's slipped out and it's 5 feet away, that still meets the requirements, right?
Yeah.
Or am I thinking that a little bit?
What happened?
would be-
So what happened last time, for a little bit of context, is that we 3D printed the CanSats and we 3D printed plastic lids, and there were 3D printed plastic hooks basically on those lids that the parachute attached to. What happened is in the flight, when the parachute deployed, it actually ripped those plastic hooks off. So our whole truss basically fell like 80,000 feet just until it hit the ground with no parachute. That's what we're that's our biggest concern, because like you say, Justin, if it hits the ground and it breaks a little bit, that's fine at the end of the day.
Okay, so you're trying to design for the possibility that the parachute fails
Yeah,
and still covering it regardless of the parachute failing.
well, not so much the parachute failing, just like the parachute exerting a lot of force when it deploys.
Last time, we didn't test as well as we needed to, and so the force that the parachute deployed upon opening completely tore it apart from the main project. So that's our kind of main concern is having everything, not free fall 80,000 feet.
Okay, I appreciate that context. That's
Gotcha.
good.
yeah, that's a good idea. So, and then again, always test to more than what you expect. Like if factors of 2 or, the amount of factors you can get above and still have it work is the better.
Yep.
But I mean, if we're wrapping up, I like you guys' Gantt chart though. I like that you guys plan for wiggle room. That's a really good idea.
Yeah.
Take more time. I guess unless people have more questions, I think I don't know where everybody else is at and their understanding on this project, but I'm a little confused so far. So this might not be necessarily a mechanical team. I'm a little more confused. I'm more just like the concept of operations for this one. and how the overall thing looks and functions?
Yeah. I think maybe, okay, well, since we're doing 6 payloads, each one has slightly different function, but
Your
we'll-
audio's kind of cutting out there. Sorry.
Oh, sorry, yeah. Since we have 6 different payloads, each one has slightly different function. So I think hopefully as we get into more of the presentations, for each payload, you'll get a little bit more context.
Okay.
Any last questions?
Are there any like final questions for the mechanical team?
Are you guys in charge of the parachute on how it functions, or are you just?
We were given one, and it doesn't really do anything besides just open at the specified altitude. So we have the data on it and its diameters and other things, but as far as that's pretty much all we have on it though. We were given a parachute for the project.
Okay. And how does it just open? It just
Mhm.
is it like attached to the balloon and it's already there, or is it something that's?
So the way it's attached is you have the leads from the like the truss that go up, they go up and meet at a central point, and then you have the parachute, and then attached to the top of the parachute is the balloon. And so once the balloon bursts, it begins falling, and once
Okay.
the atmosphere becomes thick enough again, the parachute will catch.
Gotcha. Okay. Okay.
Mhm.
All right.
I had one question I remembered. You guys talked about concerns with the lids coming off. You're going to design a custom lid as the way of solving that. Do you have any details on what that custom lid design is?
Yeah, if you look at the coolers, they came basically in 2 halves. So this doesn't show that the fact that they're hollowed out, but they are. And they're fairly tall, but basically 2 of these styrofoam pieces. What we're planning to do is take the top styrofoam piece, cut it down to the height that we need it to be as the lid, and then probably just use duct tape or some kind of adhesive to affix the 2 styrofoam pieces together. It shouldn't need to be extremely strong because there's not going to be load on it. I mean, it's not hooked up to the actual balloon or anything. It's just basically keeping the payload from falling out.
Where's the parachute attached to?
The
The
arms,
parachute would be, sorry, what, Mikey?
the arms of the truss is where the parachute will be attached to.
So
Okay.
right around here. We're
Good.
gonna just
Okay.
drill
Good.
a hole through.
Okay.
Do you know what these balloon systems, is it common for the system to tumble at any point while it's on parachute? Is it spinning and flapping all over the place, or do they usually come down pretty nicely?
Yeah, they normally come down. We haven't had any issue on descent. The ride up to ascent can be kind of violent once it hits the jet stream. The entire apparatus can literally go horizontal in the jet stream. We've actually had footage of the payload whipping up and around towards the balloon. That was part of the reason why I was like, make sure you don't have anything sticking out, as you know, as reduce that as much as possible. But once the balloon bursts, normally it's kind of like if you just imagine that the balloon bursts and you're going to have the momentum of the payload going up for a moment, coming towards the parachute, but there's normally enough length between the payload and the parachute to where it doesn't get tangled up or anything, but it'll rise up for a little bit, and once it starts to descend, the parachute normally deploys. Yeah, we've never had footage of the parachute being tangled any kind of way. It looks bad going up, and honestly, you see everything twisting around and so on, but the parachute normally deploys without an issue.
Okay, so then the lid design, are you guys hoping that it could, maybe part of your testing is going to be making sure that it can support the full weight of whatever's inside, upside down?
Yeah, definitely.
Yeah, we'll
Flips around,
be adding
tumbles.
weights to it to simulate having the full payloads.
Okay. Sounds good. Thank you.
And just
Thank you
going
for the
back, I think Ryan asked a question about where. I'm assuming it'll be at the hub, right? The center where all of these styrofoam containers meet the hub? You know, you got all these spokes in a sense coming out with
Yeah.
the clamps. Okay. Yeah, right up in that area there.
You mean like where the balloon's gonna hook, where the the hookup is?
The actual attachment, right? Because at first you pointed towards one of the legs here, one of the arms, but would it not be in this hub, the center hub where they all meet?
We were currently planning on having the hookup like on one on every other arm, so 3 hookups total between the 6 arms.
I think it's a good idea to have the hookups on the arms, because if you have the hookup just on the center, it's gonna be really prone to just rotating about that hookup point in the center. If that makes sense.
That makes sense.
Okay, so if you just have that one hookup point, it might, it could be different weights in the CanSats or a breeze or something, and I feel like it could be really easy for it to just start tipping around.
Mhm.
Yeah.
So if you spread the point outs further from the center, you should be more stable.
Yeah,
That's what
that was kind of our thought process as well.
Okay.
I think
Yeah,
in
I
the
mean,
interest of time, we're gonna move on to the other payloads right now. But if
Sure.
more people- we'd be happy to discuss this with you at a later time.
If you guys have more comments that we didn't get to, please send them in.
Okay, let me find the payload 1. Actually, does someone from payload 1 want to share their presentation?
Yeah, I can.
Sounds good.
We're payload 1. Our name is Marshmallow Sat, and this is our preliminary design review. So our basic overview of our PDR is we'll go over our team members, our general mission of what we hope to accomplish, what we expect, and our general concept of operations on our launch day. We'll also have our electrical and mechanical subsystem designs, and we'll have information on our budget and sources. What we want to get from this PDR is feedback and guidance on like different things that we can watch out for. Anything that we might have overlooked in our presentation, we want some outside perspective from people who aren't on our team, and some just general feedback on our design. Okay, so these are our team members. There's me, Elsa. We have Katie and Tegan. We'll be the ones presenting today, but these two couldn't be and present with us today. Okay, so our mission statement is our experiment will measure radiation and heat to find out what altitudes will cook certain foods without a dangerous amount of radiation. The reason for this experiment is because we want to measure radiation in the atmosphere and represent it in a fun way. We will learn about types of radiation and how they vary at different levels in the atmosphere. So basically, we're going to be sending 2 marshmallows up in our payload with multiple temperature sensors and radiation sensors, so we can measure how they affect our marshmallows. We'll also have a camera that will be watching them, so we can have a visual on our marshmallows to see how they affect the radiation and temperature affect them. So our minimum success criteria is we want all of our sensor data retrieved. This will include radiation, temperature, and altitude sensors. And we want to be able to find and retrieve our CanSat. Our comprehensive success criteria is we want to get and understand all of our sensor data. We want our marshmallows to survive the drop back to Earth, and we want to get photos. We also want our CanSat to stay as operational as possible. We don't want it to crash and break into a bunch of pieces when it hits the ground. So our expected results is we want measurement of the types of radiation in the outer atmosphere. We'll have radiation sensors in our payload to measure that. We want data, we'll be sending up marshmallows, so we'll get data on how the marshmallows are affected, but then we can use that information to hypothesize how other foods could be affected as well. We want to make an infographic at the end to just simplify and organize what we discovered with our sensors. And we also want data on the radiation levels at specific altitudes. So on launch day, this is our basic concept of operations. We'll load the food in the CanSat 15 minutes before launch because we don't want them to get damaged and we don't want some unknown variables to affect them. 10 minutes before launch, we'll power on all of our systems, and 5 minutes before launch, we'll start our data collection. After we launch, 90 minutes after we launch, the balloon will burst and it'll start descending back towards Earth. The parachute will deploy 2 minutes after that, and it'll land approximately 240 minutes after we launched it. Okay, I'll pass it on to Tegan to talk about our electrical subsystem design.
And then next slide, please. So this is our electrical design overview. As you can see where all of our sensors will go, our marshmallows and other things like that. We will have a radiation sensor that will take our radiation measurements, an altitude sensor that will take our altitude measurements, an external temperature sensor, which we will compare to the 2 internal temperature sensors that will be in the marshmallows. And then we will have a camera on the marshmallows that's powered by a Raspberry Pi, along with some lights to just kind of try and illuminate them so we can see them to the best of our ability. And all of this will be powered by a battery system. Okay, this is our power budget. The biggest draws will be the Raspberry Pi and the radiation sensor, and our lowest draw will be the pressure sensor. We're not really worried about it too much because we'll be using 2 batteries and our total is 1.0296 watts. So we're really not using like an overly extensive amount of power. And then as far as our risk matrix goes, we're not too worried. There are not a lot of like major risks that could happen. One of the more likely ones would be it would run out of power, which I discussed in the last slide is highly unlikely as far as like the amount of batteries that we will be using in comparison to the amount of power that we are using. And as far as the sensor breaking or connection breaking, we plan to double check all of them. And if we need help, we'll ask the College of Mercer AXP team to help us make sure they don't. With that, I'm going to pass it off to Katie.
So this is our mechanical subsystem design. In the top floor of this CanSat, you can see our marshmallows. The little gray boxes are temperature sensors, and those are the internal temperature sensors. A floor down from there, you'll see another little gray box, and that is the external temperature sensor. We also have the very bottom floor has our battery system. The middle floor is the rest of our sensors and all the connections we need to make to them. And then there's a little red box right above the marshmallows, which is our camera to look down at them. So most of these are not very likely. So basically, one that's somewhat likely but doesn't have a lot of consequences, the marshmallow is not well illuminated. And we put lights in there for that reason. The marshmallow inflation or the marshmallow leak, we have a plan to put either like a Tupperware or some other container around them. So if they did leak, then it wouldn't damage the rest of the CubeSat and it wouldn't be a huge problem. And the dislodged wire, we're going to double check before we have anything done. And we're going to make sure that that the wires are all nicely secured and won't just not work.
It's me again. So we plan to meet in person from March 13th to around April 17th to actually build our payload. On March 13th, we plan on combining our sensors and find or create our polling rate. And from March 13th to March 31st, we plan on working on our manufacturing final electronics. We're hoping to be about halfway done with that, but completely done with it by April 17th. On April 17th, we also plan to combine our payload with our 3D prints. And sometime between April 17th and April 24th, we'll do some kind of testing, but that's not 100% set yet. And then on April 24th, we plan on doing the launch, which will mostly be taken over by our college AXP members. And as you can see, this is our budget. You can see our total in the right-hand corner, and in the second column, you can see the prices to each item in the first column. We're not too worried about prices with this because most of the stuff we already have currently, but our most expensive thing would be our pocket Geiger radiation sensor type 5, and our least expensive would be our 1-wire ambient temperature sensor, which will total at $780. with that being said, does anyone have any questions?
I do. And it's not a question, it's just a comment, recommendation. Great presentation. Your floors, if you would go back to that slide, please, who's ever doing, yeah. What type of material are you using for the floors? And the reason why I bring this up is because the styrofoam container itself, and this is just from experience, a lot of light actually penetrates through it because it's just white styrofoam. So it's fairly bright on the inside. So the camera may work. So it may depend on what you're using to create these floors, if whether or not you need light, because you may put light in there and it may be too bright and it may wash out everything. So definitely that'll be part of your testing anyway to what works and what doesn't work. But if you could keep whatever you're using to create those floors, particularly the top floors, maybe another styrofoam white or some type of clear plastic, that'll help greatly. And you may not even need the light, but you would need the styrofoam outer container for it. And then also, and I know this is just a drawing here, but it seems that this is suspended. You know, is it going to be flush with the bottom of the styrofoam container that is in, so that you don't have possible movement in there up and down also?
Yeah, we'll probably put it towards, we'll probably have it flush with the bottom because, yeah, that's a good point. We don't really need space there. So this is just our first drawing that we have.
Right.
But it'll probably we'll have a lot of changes probably by the end.
But yeah, as far as your lighting, make sure you test that out, because you may not need the light after all.
Yeah.
So for my question, it was about the launch time frame. Could you go back to that slide?
This one?
So 15, you have loading the food into the can set. Do you guys already have approval that you're able to do that right before?
This is just our general plan. It's not like set in stone. This is just kind of generally what we want to do. It might change as we get like more in-depth planning, but what we want to do is load it as close as possible to the launch, so other things won't affect the marshmallows, because we want just no outside variables to affect them.
Yeah, so I know for one of the rocket launches we did a couple years ago, a team was planning on loading their payload, I think like a couple hours or like the morning before, where really we didn't have access to the rocket for I think like a week or two. So they kind of figured out pretty late in the game that they weren't able to do things on the timeline they thought they could. So I would just make sure that you're able to do that. Or else just making sure that, you know, whatever you do to prepare the can sat is going to get rid of those variables.
Yeah, thank you.
I think you guys are doing good with that too, because you're presenting this in your con ops, and I think is Professor Nero, you're going to be running or helping run the show about all the pre-launch preparation. Is that right?
Well, yeah. Well, I hope to still be there in that location. Actually, I'll be talking to my class about that today, as I shared with y'all before. But yeah, 15 minutes prior is not bad, honestly. The thing is that everybody just truly needs to know this. So this team, yes, you will know 15 minutes to launch. If we're launching at 10 a.m., 9:45, pack that stuff in, because we need to do the rest of what we need to do. Okay. Because you will basically affect the group's launching of this, because you're affecting the apparatus, the whole launch platform. So to get it in, to have it ready, because maybe whatever that floor, that house, and I like how y'all described it as the floors, whatever that is, maybe that's all you need to do is like literally slide that into the styrofoam container at 15 minutes prior. So you can do whatever you need to do with that entire assembly that you have that goes into the styrofoam assembly. Take your time, do whatever you need to do with that. But at 9:45, in a sense, it needs to be able to go directly into the styrofoam, and the CubeSat group can seal it off. And now they're not worrying about anybody messing with the payload. They can do whatever they need to do 15 minutes prior to launch.
I would say if possible, maybe even have like 2 marshmallows in already, and then at 9:45 go in, swap out the marshmallows, so you don't think you have more time when really you may not have that. I would say make sure to have it done and then swap out the marshmallows, right before would be my suggestion.
That's a good plan.
Oh, go ahead.
Just real quick, on your the power that you were going to need, I didn't see that you included the camera, so I just want to make sure we're okay.
Yeah, so our camera is going to be run by a Raspberry Pi, so the camera itself will just draw power most likely from the Raspberry Pi, if that kind of makes sense.
Are these max powers then that you're expecting?
Yeah,
Okay.
Yeah, sorry.
That's fine. That's fine. I guess I have some comments, I guess, with your guys' risks. First, I want to say that it's awesome that you guys are doing this and thinking through all this stuff beforehand. Because I'll tell you, especially when I started doing stuff in engineering, like I didn't even get to this level and had to learn along the way. So it's awesome you guys are doing it. When you guys are doing risks, especially stuff that's more like these orange and yellows, I just always make sure to have like a plan on how you're gonna like make sure that those aren't actually going to be problems. And for your guys's, that would be kind of like maybe like you're running out of power, right? So you kind of just have like an estimate for how long you're going to run. So maybe try once towards the end, when you guys have stuff working, have it sit down and run for that full length, and then make sure that it's still going, or if it needs more power, or and especially since this thing's gonna get cold, maybe putting it in something like a fridge or freezer if you're expecting similar temperatures, in case you're worried about temperature affecting the battery. Like those are all good things you guys can do, especially beforehand. And always plan for these tests. When you do these tests, always plan to have time afterwards to make fixes and changes.
Right. Yeah, and I don't know if you, this particular group had a chance to see the comment by Rachel Welch in regard to the cameras, proximity to the actual marshmallows. You definitely want to do some tests with the camera prior to see what that length needs to be, that distance needs to be, to get a really good shot of your experiment on the inside, because yes, it can't be too close, of course. And also those things may impact how you do this. But what's really neat about what you're presenting here is that it's its own self-contained unit, and it just goes into the styrofoam. So you have a lot of flexibility, I would say, in working a lot of that out without necessarily being impacted by the payload apparatus itself. So if you're working within those within the criteria that they give you as far as that interior space, the diameter of the inside of that styrofoam container, and things of that nature, the height you're working with, you all have a lot of opportunity to get this thing to nail it really well. And everything that we just shared about the risk factors and the power consumption, all of that, great advice.
Thank you.
I had a couple questions on your project. I also think it's very interesting, and I think you guys have done a good job presenting it. Regarding starting with the risks that you have here, and your sensors, since your minimum requirements is having radiation data, if you guys are you guys concerned that radiation sensor that you bought, if you're gonna have a failure there and that creates makes it so you can't meet your minimum success criteria, you might want to have redundancy. I like how you have more than one marshmallow in there and more than one sensor, and I believe more than one camera looking at it. So that's a good way to mitigate that kind of risk of sensor failures, because if one of them goes, then you at least have the other one. But I guess my question would be for you is it worth, do you have the space, the cost, and the power to have a second radiation sensor in there if it is that critical to your project here?
Yeah. So since we're not using a bunch of power right now, I'm sure we could fit it in our power budget. I don't know much about, since it was our most expensive sensor at $60. I don't know if we can get another one or if we
Yeah,
but
I understand.
yeah, if we can't, we'll definitely make sure it's protected very well since it's our most like important to our whole experiment. We'll definitely make sure before launch, like we'll make sure that it's secured well.
That's
so
good.
we can mitigate it as much as
I
possible.
understand that the balance you always have to make is the risks and the cost and everything else. So I understand that. I had two other things I was going to ask, but I didn't want to cut off Dr. or Professor Nero. I think you were saying something, or nope.
You're
Oh, okay.
good. No, and
Oh,
that was
okay.
a great point.
Yeah. I have a question on the radiation sensor itself. You mentioned that it measures different types of radiation. Is it actually measuring different types of radiation or amount of exposure?
Well, I think Joel is the one who knows the most about it. He has our radiation sensor now. We want to measure different types of radiation, but if it's not possible, we'll be good with just one type. What we want to do is just see how at least one type to see how it kind of like varies throughout the atmosphere. Is what our general experiment is.
Okay, and that makes sense. I think it would be helpful if maybe that talking point on what you're measuring there is a little more clear for people, especially since myself, I don't have a lot of experience with determining radiation exposure. I've had to deal with electronics a little bit, but not on the, I think, the degree that you guys are looking to, but just having a little bit more of a story there would be helpful for anybody that's trying to understand your project here.
Yeah.
And so either way you go, that I think that's fine. And then my last question is on your process here. I'm curious of, do you have a plan or do you know what you're going to do to try to separate, you're measuring heat on a marshmallow due to rising in altitude. Are you measuring what heat is being generated by your onboard electronics so that you can separate out your devices from the actual environment that you're exposing it to? Because I believe you guys are more concerned about the environment, gaining altitude and the radiation exposure and cooking the food, not necessarily your electronics cooking the food.
Yeah, so before launch, we'll definitely, since we should be running to see how the power checks out, we should be measuring that. So if we do get a little bit, we put them on different floors apart so we can make sure that they're not, hopefully not affecting it. But if it does, we'll definitely try to find that out before we launch it so we can subtract whatever the temperature is that that might be coming from the equipment instead of just the atmosphere.
Yeah. Anything you can do. I think someone mentioned running a full, maybe full system test and making sure that your system can handle the power. I think maybe another part of that will be, what happens to everything that you have in there. If it's a full, what happens to your marshmallows? What kind of temperature do they experience? All your sensors. Make sure you log all of that, so then when you do this test, you can actually separate out the effect of your devices on the ground and from when they're actually in practice.
Then you can always add like a disc of styrofoam inside of your CanSat to mitigate any heat generated. So
real quick, this is all good feedback, but we do have to keep moving on to other payloads. So I'm going to ask you guys to cut it short now.
Gotcha.
If someone from payload 2 wants to share theirs.
I can.
I want you guys to know that this happens all the time, even in NASA PDR presentations. That always goes over, people talking and asking questions.
Well, I mean, I think a lot of people here would be comfortable going till 3 or 4 p.m. But it's just I don't know that'd work for everyone.
No, I agree, and it's good to keep it on track. I'm just letting you know that this just always happens. So
good to know. Good to know.
I've been a part of reviews that have been 3 hours over or more. So.
Sorry, just. Hello, we are Team 2, otherwise known as Team Sanic, and here's our PDR. Our mission is to receive feedback goals and basically show our payloads that we plan to launch in the springtime. And here's our teammates on payload 2. For feedback, we want to receive feedback about possible mishaps and like things that we could run into trouble, and also potential like things that could help us along our way. In the environment, our mission statement is in the environment the HAB provides us. We plan to test the effects of radiation on the foxfire mushroom's bioluminescence, along with like the mycelium's ability to block radiation, and as well as see how well we can manufacture and kind of like build a perovskite cell. Our payloads are kind of like stacked in kind of like a shelving manner, and we have the foxfire payload on near the bottom, and the radiation one on the top, and in the middle is kind of just all the sensors and wires. For our general risk matrix, number 1 is a heat system failure, which isn't too very likely, but there's lots of consequences if it goes wrong. But heat systems have been done a lot, so we shouldn't run into too many problems with that, and we'll have to do lots of testing to make sure it works well. For next one is that the perovskites fail, like they don't collect power and the panel is damaged or like falls off. For this, we'll just have to make sure that everything's secured and still do more testing. So it shouldn't be too big of a deal, but we'll want to make sure that that doesn't happen. The third one is that our mycelium mushroom dies. And myceliums are kind of a they're kind of a sturdy mushroom. They don't die easily, but there's still like a chance they could die. This would probably happen if they like die from radiation or like heat system failure. And we mainly still just want to like do lots of testing, and we have ways to protect it from dying, so this shouldn't be too big of a risk. And the fourth one is that the glow mushrooms die, which they're a little more likely to die than mycelium, and that wouldn't be good. But we have systems set to like protect it from dying, so we'll just have to do lots of testing to make sure it works. And the fifth one, which has a pretty low probability of happening, but kind of high consequences if it does, is that our data system fails to collect everything, which means we just lose all our data information. Luckily, like literally every payload uses data collection, so we have lots of resources to look towards and just more testing to make sure that everything works well. Our minimum success criteria for the foxfire mushroom is that we can reserve bioluminescence and to make sure our data is retrieved. For the mycelium, it's basically the same thing, reserve like the radiation effects and retrieve our data. And the perovskite one is that our panels don't fall off and some power is generated. And then, of course, we want to find and retrieve our payload when it's over. Our like optimum or maximum success criteria is that all the mushrooms survive and we can observe lots of effects from what we're looking for. And for the perovskite, we just want to make sure that it's efficient and it works well. Around 15 minutes before the launch, we'll load the mushrooms onto our payload. In 10 minutes, we'll turn on the power collecting systems, start our data collecting and perovskites. Then it'll be launched, and then it's just standard. It'll just go through the air until it eventually lands back on Earth and it's recovered. Then originally the bioluminescence payload part was supposed to be covered by Caleb Rowe, but he's gone. So instead, Evan Tyler is going to present it, and I'll pass it on to him.
Hi, I'm Evan Tyler, 13 years old, go to Skill Middle School in 8th grade. So this is our bioluminescence mushroom payload, and the type of mushroom that we will be using is Panellus diptychus, more commonly known as foxfire. And the reason we chose these, it was easy to obtain, it had bioluminescence which fit our description, it was cheap, resilient, we know how to grow it, we have lots of resources to understand how it would prosper the most. So yeah. So our goal is to test the effects of radiation on a bioluminescent mushroom in the atmosphere. And we also plan to test how radiation makes it glow brighter, softer, if it even affects it at all, even just cancel out any kind of bioluminescent. And so for our experimental layout, we are keeping it in an atmosphere controlled box, which is the yellow bit on this diagram at the bottom here. The photoresistor, we're using it to measure how much it changes in the output of light. So in the center, we will have the Foxfire with the photoresistor beside it, and it will be surrounded by yellow insulation, or the insulation. So this is our risk matrix. So at number 1, we have mushrooms are killed by radiation, which has not very high probability, but it's certainly up there. And the consequence wouldn't be too dire, but it's quite probable. So we have to keep an eye on that. Mushrooms glow is too faint for photoresistors, which is at number 2. Very low probability, basically next to none. But the consequence would be high because we wouldn't really be able to extract any data whatsoever. And then photoresistors shift or malfunction, also extremely low probability, high consequence. We will not be able to see much, we won't be able to measure anything, and it would put a damper on our whole experiment. And finally, at number 4, the mushrooms die due to atmospheric effects. Higher probability, a little less consequence than 2 and 3, but we have insulation and whatnot and other means to save it from any unwanted side effects of space. And then I will pass it on to Gavin again for the mycelium payload.
Thank you. Oops. Okay. Our type of mushroom is basically the mycelium, which isn't actually a mushroom. It's more like the root parts of the mushroom, like what starts the growth of the mushroom. We chose it because it's like easy to obtain and it's resilient. It's also safe to work with, so we should have, and it grows really fast, so we'll be able to grow it in time for our payload launch in the spring. Our goal is to using radiation sensors. We want to test the mycelium's ability to kind of like in a radiation present environment to like see how it can like block out radiation. We kind of borrowed this idea from an old CubeSat one that we ended up throwing out. And then the knowledge gained from this could also help like future astronauts like mitigate radiation on missions. For our experiment layout, we'll also have an atmosphere controlled box just like the bioluminescent one. We'll have 2 radiation sensors. One will be kind of like outside the mycelium. The other one will kind of be like enclosed around the mycelium to see how well it blocks it out. For our risk matrix, number 1 is that the mushrooms die from radiation. They're pretty resilient, so this isn't too likely. And even if they do die, that's still data that they do die from radiation. It's not like our wanted outcome, but it still like shows us the effects of that. Number 2 is that the radiation sensors fail, which isn't very likely because lots of these things, many people have worked with them, so I have lots of information to use on that. Also, if the one outside the mycelium dies, we also have other radiation sensors across other payloads that we'll be able to use data from to compare. And 3 is that the electronics fail, which shouldn't really happen, but it has a high consequence if it does. We still have, like I said earlier, we have other data from other sensors around like across other payloads that we could use, but we still wouldn't want this to happen and it shouldn't. Next, I'm going to pass it back to Evan to talk about the perovskite part of our payload.
So this is our last main payload for the HAB, and yeah, we will be using perovskites, which we will also be using in the future. So this is more of us trying to document how they work. That way we can use them on the CubeSat that we're also manufacturing. So they're extremely efficient. We have resources to understand how they work, and we are buying the supplies. That way we can build them from scratch, and hopefully we can see how they work when they're in the atmosphere. So our goal, we're planning to test solar cells in an atmospheric environment and gain information. That way we can have more information when we launch our CubeSat and our endeavors in the future, along with any other people who'd like to reference our payload and see how they might function in space. So this is our experimental layout. On the left, you can see a small diagram of how it'll be arrayed. The perovskites will have one on the outside of the payload and one on the inside, just to compare how they yield different results. The mushrooms, so the mycelium and foxfire, will both be in the center, and then the outer casing is our insulation for the mushrooms, and it's going to be what's holding all of our stuff together. So this is our risk matrix. At number 1, we have a semi-low probability but higher consequence thing where the solar cells don't perform as anticipated. If our data is wrong or resources we've looked at are faulty, then it could be bad, but we doubt it will happen because the probability is quite low. To mitigate this, we're going to be testing a lot. Most of these can be ironed out by just testing often and frequently. That way we can see how they function and get rid of any unwanted side effects. Number 2, damage occurs to the cells during the mission. Also low probability, but higher consequence. If damage happened to the cells, that'd be pretty bad. But what we are planning to do is get some kind of casing, either like a solid container or spray on an adhesive to sort of like a primer just to save the solar cells from any damage. 3, mechanical failure. If anything breaks while they're on Earth or in space, anything to the mountings and they fall off, that would be quite bad, but very low probability. Our mountings are quite solid and sturdy, so that shouldn't happen, but we are again going to be testing a lot. That way we can get rid of that risk. And finally, the solar cells are built poorly. We are going to be building these ourselves, and we're quite new, but we have lots of good resources and information. That way we can build them to the best potential. And again, testing, really big thing. We're going to be using it to save us from any unwanted side effects. And then I'll pass it on to Elijah for the electronics.
Hello, I'm Elijah Wongwalker. So for logic controllers, we're going to mainly use a Teensy 3.0 microcontroller, and it'll be saved on the SD card to the microcontroller. So our power budget is about 10 watts, but for the entire 4-hour mission, adjusted for safety for 1.2 safety factor. So this is our diagram. So the perovskite payload, and so the perovskite payload would be perovskite cells with the voltmeter and ammeter, and foxfire would be mushroom, the light sensor, the temperature sensor for radiation. The mycelium payload would be the internal radiation sensor with the external radiation sensor on that too, with the temperature sensor too, all going into the Teensy with batteries hooking that up, and then there would be a heating system with batteries powering that too. So the atmosphere control and heating will be attained by creating an airtight container in mushrooms with a sealant or something like that. And the heating will be obtained through heating pads like below. So that's our risk matrix. So the first one is if the heating just fails entirely, but we will be testing to make sure it's not too probable, but it will be terrible. Number 2 is data collection and storage fails. It's even less probable than that, but also very bad. If the batteries fail, then that's again the same area. And if the microcontroller and sensors overheat or freeze, also be in the same area. But we will be testing these to make sure. If the connection breaks, it's not as bad, but it's still pretty bad. But we will also be testing these and adjusting to make sure that we can do it in the atmosphere and pressure.
So I will also be covering the manufacturing payload and how will we be covering that. So this is our budget. We're going to be using Teensy's, micro SD cards, perovskites, which is a larger chunk of our budget, and then other components just to measure radiation and other components that we might need to fulfill our experiment. So the total would end up to be about $313, more or less. We're still adjusting this, so that can change. We might still be adding things, and we might still be tweaking different brands and whatnot. So this is our schedule. We'll be taking time to grow the mushrooms, which have already been started, and then test things, test the sensors, test perovskites, test the holding mechanisms, and then finally we'll be building and assembling along with 3D printing any parts that we might need. And then finally, more testing just to fix anything else that might be underlying. And then finally we will launch, and I will sit here for a second, that way you can look it over if you'd like to do so.
Great presentation. Just quick question, and this goes to, the UNL group. I see that they have an attachment to perovskites, did I say that right? On the exterior of the styrofoam container. Will the students have access to these containers to make those assemblies and then I guess hand them over to you so you can then put the clamps on them and so on? How will that work out? How is that scheduled? Is that a day before type thing, kind of going back to what Beth was talking about earlier? Is that a day before situation that they could do that, or will they be attaching it the morning of?
We're actually planning to start having build days with everyone in person. I think the first day for that is March 13th. So we're going to have like a series of, I think, 6 build days at the Innovation Campus where everyone will get to assemble their payloads like that.
During that build, they'll coordinate how they're going to attach, and they will attach the perovskite panels prior to the launch date.
Yeah, that we'll have everything. So the perovskites will have to be attached prior because we can't just quickly tack that on 15 minutes ahead of time. So yeah, those will be on prior, but then everything else will kind of go the same as every other group, where they load it right before the mission starts.
And with that being said, will it have enough lead time for them to do their proper testing, structure rigidity, that things aren't loose? Will they have enough time? I guess you're going to have a mini schedule that will fit into this schedule, maybe, for them to do that type of testing ahead of time. What works best? The best way to adhere it, to attach it?
Yeah, for the exact details, we don't have everything quite planned yet. But yes, we have multiple of pretty much everything. So we were planning on doing the drop tests with, some wine coolers, but then working on one ourselves. So as for the testing schedule for that specific part of it, we don't have an exact black and white thing done yet, but yeah, we're working on that.
And finally, we have our payload success preference. So this is the order in which we organize our payloads in ranking of importance. So at number 1, we have the perovskite payload. It takes perhaps the most work, and also it's we need to use it for our future CubeSat, so that information will be prized. And then after that, we have the Foxfire payload, and then finally the mycelium payload, which is about the least amount of work and also the lowest on our preference list.
I think that's as far as the side goes. So next is questions, if anyone has those.
I have some questions. I think you guys have a lot of interesting ideas, a lot of good ideas. Am I interpreting this last slide right in saying that you are planning on doing all 3 of these, and that this preference here means if you struggle, say, with the mycelium payload, that you will drop it and focus on the perovskites and bioluminescence?
Yep, in case we get a sudden, there's a time difference, or if something goes wrong, we will prioritize perovskites over the other 2.
Okay. Are you is the process that you're going through is going to be focusing pretty solely on the perovskites, and then once you complete that, then move on to bioluminescence?
Most likely, since it's our most important one, we'll be focusing on that. And then the other 2 are pretty easy. So we're just gonna finish those up after perovskite.
Okay. I think you guys have a pretty ambitious project here with the 3 projects here. I'll say that does concern me just a little bit, but I am comforted in knowing that you have a priority here. You know that you'll drop things if you need to. Things can always end up being more complicated than you plan, and almost inevitably will be that way. So it's good to think about, what you really want to make sure to accomplish here. With the perovskites, I was curious, what's the rationale for testing a panel on the outside and a panel on the inside?
Different amounts of solar radiation and different amounts of just sunlight that hits the perovskite might change it. So like, let's say we're in a satellite and like a big satellite and there's solar cells on the inside. How will those react differently to ones that are actually like exposed to space atmosphere?
I guess I'm a little confused. Are there perovskites? Perovskites are always going. I've never heard of perovskites being mounted internally to a satellite. So, is there an example that you guys have of solar panels being used in that manner?
I'm not sure. We're just more so using it that way we can compare 2 different environments.
We kind of heard of them collecting a little bit of light in like almost like nighttime like settings, so we wanted to like test that out more.
Oh, you trying to evaluate like low light power generation?
Yeah, kind of like that.
Okay, that makes more sense. Thank you. And I'm assuming I saw photosensor or photoresistors on your part list. So I'm assuming for each panel will have a partnered photoresistor so you can measure how much light it's getting. Is that right?
I think the photoresistor was for the bioluminescence payload to like observe that.
Okay. How will you determine efficiency then of the solar panels?
I'm not entirely sure. I think Elijah was on the mechanical electronics part, so I'm not entirely sure how we might do that.
I could try. We determine the efficiency, I'd say, by like hooking it up to something that would need charged and seeing like if it charges a decent amount with the outside, or comparing to the inside if it charges any.
Okay. I'm thinking more along the lines of, if you happen to rotate, the payload rotates around, it's not facing towards the sun. I understand they get indirect sunlight, but this thing might be spinning around and you might see pulses of activity from it. Might be interesting to know, is it because it's getting direct sunlight or more direct, or it's been shadow the whole time?
Well, we've heard that you can collect indirect sunlight, so that's also something that we could be looking for.
Might I ask or recommend, I would say, that you could possibly put both on the exterior and have one on the side, which would be, I guess, horizontally, and then maybe one facing downward and maybe even a third facing upward. So that way you would be able to identify which one was up, which one was to the side, and which one was down. And you would definitely get what you're talking about as far as indirect sunlight, especially for the one going down, facing downward. And you can extrapolate from there between the 3, as well as what Justin was sharing about the rotation and the movement, because it will go through a lot of that.
That's a good suggestion. We might have to look into that. Also, I think the perovskites are being attached to a voltmeter. That way they can compare the 2 potential differences.
I guess one thing he's talking about that was wanting to evaluate like how much light is being shined on it versus how much was actually turned into, useful energy. So like having a way to quantify how much light is being shined, like having extra photoresistors, right? That are next to the solar panels, and those can tell you, well, the solar panel got this much light at this time, and then you can see well how much voltage was generated based on how much light it was getting.
Oh, and that's a question I do have. You say that your panels will be connected to a voltmeter. How are you recording all of this? And I say this only because I had students who they struggled with trying to program or to get their Raspberry Pi, and they weren't coders, okay? So, but they struggled with finding a way of getting that voltmeter reading and storing that data so that they could have it later. As so they went about this rudimentary way of like having the voltmeter in the pod with a camera on it, and they recorded it that way, which of course was beyond tedious as far as data collection, just looking at a video for 2 hours and recording what you saw in the video. So how are you doing that as far as having that data when it comes back? You could just hopefully pop it into a laptop and see your voltages.
I'm not entirely sure. I'm not a very big electronics guy, but our perovskites will be attached to the voltmeter, then the ammeter, and then a teensy, and then the batteries will be powering the teensy. I'm not entirely sure how the things work, but that's my guess. I'm sorry.
If I could pop in for just a second, I think the plan is to use the Arduino Teensy as the voltmeter because it has an analog read function, and then just get the ammeter.
Yeah, good.
So yeah, that's a good way to do it. I don't know who's going to be your programming or whatnot, but usually you have what he said, an analog read, so you just have it read the voltage, and then it saves it to something called a comma separated variable list. And what that'll turn into, sorry if I'm getting too complicated, but it'll make it like an Excel sheet. And then every new box, it'll pretty much make an Excel sheet where every box is the next reading that you guys would do. So, but that's just a general idea. What was that?
Those readings should all have timestamps with them too. Make sure that is included. That'll be very important for figuring out, evaluating your progress.
All right, moving on. Again, good feedback, but I think it's time for payload 3. Does someone from payload 3 want to share their screen?
I can do it.
Okay, so today we'll be reviewing over our preliminary design of our payload Pi. So our overview is our mission statement, the objectives, what we expect in our results, the nanosat payload Pi specs, how much power we need, and how much everything costs, and all the concept of operations and all the risks that. So our mission statement is our high altitude balloon project, or our payload Pi. And we're going to be testing and learning more about the high atmosphere, specifically radiation, but we're also going to be testing the accelerometers, the temperature, the voltmeters, and the ammeters. So our main focus on this project is specifically trying to learn more about radiation sensors and testing how the efficiency of silicon solar cells in the high level of the atmosphere. I'll be passing it on to Robert.
Our objectives are to see how low-cost CubeSat parts react in high atmosphere. We don't want to spend too much on parts for this, so we can save up more CubeSat, of course. We want to have like a pre-test to learn how things might need to work when we are doing our CubeSat in space. So we can also get a better understanding of things that could end up happening when we launch our CubeSat, and also learn to work together better as a team and what our strengths and weaknesses might be. Next slide. Our expected results, of course, is that the NanoSat will be successful at obtaining the radiation recordings. If the NanoSat does do something strange or unexpected, we'll be able to take that into account when we send our CubeSat in space. We will be using a NanoSat to accomplish this, which is somewhat like a small version of the CubeSat. I'm pretty sure it's 2 inches cubed. Inside of the NanoSat, what's already built into it is a thermometer, accelerometer, a carbon dioxide sensor, and it can be coded in Python. We will be connecting the NanoSat to silicon solar panels, which came with the NanoSat, and radiation sensors. For when we put in the styrofoam cooler, we'll put the NanoSat inside of it. We'll attach silicon panels on the outside of it. We'll have radiation sensors connected to the NanoSat in some way. We have an Arduino Teensy, and of course, it's all inside the cooler box.
So here we have our components list. You can see there the 4x4 keypad there is representing our silicon panel. And then that Arduino board there is representing our NanoSat. And this is just kind of showing you how we would be setting it up with having our solar cell going into our board, and then all of the power and how it might be wired up. And then here we have our power needs. You can see our total is 9.03 watts, but obviously, of course, these wattages are estimations of how much we'll need. And our main power supply is actually not our silicon panel. Our main power supply will be our batteries. And then we have here the money budget. So you can see our total cost overall is going to be $221. And then you can see the different items that we have and where they're from, and then just the different prices and quantities.
For our concepts of operations, first when we launch, right before that, we will start collecting the data, and then when the balloon reaches like its maximum altitude, as shown from the second one, it will start the balloon will pop and it will start to descend with a parachute, and then after that we will retrieve the NanoSat. For our risk matrix, if the acceleration sensors or the thermometer don't work, then for that we will just try not to like let that happen, like double check everything. If it does happen, consequences aren't that high and chances are pretty low, so that's not like a huge deal. If the payload breaks off the balloon, that'd be really bad. So to stop that from happening, we'll test the hooks and like everything that the connects the payload to the parachute. If the wiring doesn't work, of course that'd be really bad. Not too high of a chance of happening, but something we can do to fix that is just like simple things like just checking it over beforehand. So that shouldn't be too hard to keep from happening. And if the data gets corrupted, pretty bad, and chance of happening isn't like too high though, so we should be fine there. We can always test it beforehand to make sure that doesn't happen. And for our secondary mechanical subsystem risk matrix, we have if the silicon panels break, that'd be pretty bad. So well, it wouldn't be too bad, but and chances of happening aren't too high. But to stop that, all we have to do is really just like reinforce it, make sure that it's not like weak, like not like broken in any way. to keep it from falling off, we can, you know, make sure that it's fully stuck, like fully on it. If the radiation sensors fail to work, that would be pretty bad. But to stop that, we can always just test it. And power supplies failure would be really bad, but shouldn't happen, seeing as we have the batteries and we have more watts in storage than we do in use. So we should be fine there. These are some places that we found some of our information from. Any questions?
I was a little confused. So your electronics that you're planning on using, so you say Arduino Teensy, so are you using a Teensy board or using like an Arduino Uno? Because I was just a little confused with the picture you guys had for your wiring diagram.
Yeah, so we were using Tinkercad circuit designs, and they don't really have nanosat in there, so we had to improvise, and so we used an Arduino board. You can see if you want to go back to the component slide, Dylan. We have there written we're using a Arduino Teensy and a nanosat. The Teensy isn't actually really pictured there, and that Arduino Uno board there, as you said, is the nanosat.
Okay. I gotcha. Okay. The next thing I have written down is you guys have some stuff that you're mounting on the outside of the foam cooler part. I don't know what slide that is. Yeah, there you go. So one thing here I'm worried about a conflict is the mounting that the mechanical at the very start has. If they have a clamp that's already pretty tight around it, there might be some interference if you have something mounted where the clamp's going to be. So that's what I'm just saying to watch out for.
I'm pretty sure it won't be where the clamp is. The panels that we'll be using, I don't think are that big, so they probably won't interfere with the clamp or anything. So.
Okay.
Sorry, it's a bit big on that picture. We made that before we had the actual image of the silicon solar panels themselves.
Yeah.
So.
I understand, especially this early when you guys are making stuff that you kind of just have to use the best what you have for pictures, and so if that's not a problem, then good. Then good.
And just a quick question, and this is for all groups. What's the plan in this particular case to adhere or to secure your nanosat to the bottom of that styrofoam container?
I don't think we really have a set plan for connecting it to the bottom of it. We're probably, yeah.
Well, it needs to be secured some kind of way.
Yeah.
Right?
Yeah.
You could use just like a hook, I guess. I don't know. We don't have anything planned for that. Yeah.
Well, we'll need to come up with something to connect it there. But yeah, we should have something to connect it. It will be connected to the bottom. We'll make sure to do that.
Derek, you've worked with these styrofoam containers a bit. Do you have a recommendation?
Well, several things. I mean, like literally students have don't use bubble wrap, because bubble wrap, due to pressure, all the little cells will explode and you're just going to have a whole bunch of plastic and everything will just jostle around in there. But I mean, honestly, you can stuff it. I mean, I've had students use newspaper. Newspaper works just fine and so on. But you can also use zip ties. You can run a zip tie through the base. Also, I have one right here. These little things are amazing. There's zip tie anchors. I don't know how well you can see that. These are zip tie anchors, and you can get them on Amazon. It's like you get 250 of them for like $10. But basically, you can see it has like a 3M coating on the bottom. And when you peel this green surface off, it holds really well, even to styrofoam, because styrofoam can be a little funny with certain adhesives. Certain types of tapes don't do well with styrofoam, but These things have worked really well. I've used them on the exterior of several, and I haven't had to replace them yet. And you can run the zip tie through it, as you can see the little slots, and tie it to whatever, pull it as tight as you want. But these things are amazing, and they're super affordable and very functional. Zip tie anchors.
Thanks for the heads up.
Yeah, that does look very cool.
I have some questions for you guys. You mentioned in a couple places throughout the presentation you have radiation sensors plural. Do you guys have more than one? I just saw one in your purchase, your cost breakdown, and it kind of breaks, that question kind of opens up to the rest of your sensors as well. Do you have more than one, or like one temperature sensor, one accelerometer, and so on?
The accelerometer and thermometer, those are like built inside of the nanosat, I'm pretty sure. So like those aren't a separate item. And then for we only have one radiation sensor. And I'm not sure if we were going to connect both solar cells, but technically we do have two silicon solar cells.
Okay. In your risks, in a couple places you mentioned the sensors kind of being a sensor failure kind of being up there. I saw another spot. Yeah, radiation. Maybe that was the only one I saw. Yeah, I'd say just as was mentioned with one of the other teams, anytime you have risks that are in that yellow, orange or so, make sure you have kind of concrete plans for addressing them in some way, shape, or form. As we recommended one of the other teams to, especially with like sensors having multiple. But as all of you have been talking about radiation sensors, it seems you guys most likely could piggyback off of each other's radiation data. You might not have to all have multiple radiation sensors if you guys are sharing data between each other. I think I had another question. I'm forgetting at the moment, but I think those are the two recommendations I had. Or questions.
Well, I just wanted to say about the sensor failure thing. Dr. Nero actually messaged me earlier in the meeting about saying that his students are measuring data as well. That will probably be similar to what we're doing. So there's a little bit of extra recursion there we can use.
That's good. That's good that you guys can all do that. So that definitely helps, takes the stress off of each individual payload in case one of theirs fails. You don't have to build in that extra redundancy on their individual payloads and pick up their costs and their power and so on.
I noticed on the D batteries, the amount of money you were planning to spend seemed kind of high. That I'm assuming that $35 for 9-volt batteries, I'm assuming that some of those are for testing. You're not planning to load that many 9-volt batteries into your payload.
Yeah.
Yeah.
Part of that price is also because those were the rechargeable kind, and it comes with the charger. So that's part of the reason why it is so much more expensive than would probably be a normal D battery.
Okay, good, because I was saying regular D batteries, and I thought that's heavy if it's that much.
I remember the other comment I was going to make. I'm going to make a same recommendation to you guys that I made to the other team with the solar panels. If you're measuring efficiency, it would be good to have a photoresistor or something on that's telling you how much light your solar panel is actually getting, so you can understand, measuring your efficiency versus being in sunlight, indirect sunlight, and complete shade. That'd be good to have an understanding of that.
So is that all the questions then?
If that's everything, then I think we can move on to the last little bit of the meeting. I think, Mikey, you want to talk about the heating system briefly?
Okay,
Yes.
real quick. I do have to part. This has been wonderful. I'm glad I was able to see all the presentations. this is good. I'm very hopeful. I'm excited about this. Y'all are doing a great job. Definitely UNL group in guiding, these high school and middle schoolers. This is awesome. Good stuff all the way around. Justin, good seeing you. And definitely Sally, Karen, appreciate you all. Everyone take care. And I guess if we have another meeting between now and then, see you then. And if not, I guess I'll see you on the 24th of April.
Thank you.
Working with
Good seeing you too. Take care. I might have to say for myself too, I need like maybe a quick 5-minute break to use the restroom here, but I'll definitely be back.
Right, sounds good.
Do we want to have a 5-minute break for everybody?
That makes sense.
That would work well for me, yeah.
Okay, let's do a 5-minute and come back at noon or a little bit after.
Awesome. See you all then. Okay, it looks like most people have trickled back by now. Mikey, do you want to do the thermal presentation?
Yeah, so let me share my screen. So the special systems sub-team designed the kind of internal structures for the payloads as well as the thermal control stuff. Like my Zoom controls will get out of the way. So for the interest of time, we'll just go over this part of it. So obviously the goal is to keep the entire HAB mission thermally controlled, and really that means not dipping much below freezing, because that's about when the electrons begin to get damaged. But like with payload 2, there's some stuff that we really don't want to freeze altogether, so we want to keep it at a pretty solid temperature. Somewhere around room temperature would be ideal. Thermal control is attained using 2 small steel mesh heating pads, and those are actually what this is right here. Then each of the system is a standalone, and so we'll be manufacturing 6 of these thermal control systems, each to be ran with a Pro Micro and Atmega Pro Micro microcontroller. It's a pretty simple design, as we see right here. So each will have its own batteries as well as controller, and a temperature sensor inside the payload will give feedback of what the ideal temperature is, and we'll be controlling the temperature of the pad using solid state relays. And as for the power budget, the company that produces these doesn't give a lot of data as for the kind of power actually consumed by the heating pads, but given the data that was given, which again isn't very much, and some basic measurements of our own, this is an estimated graph of what the power and wattage will be used around the temperature. So taking what we anticipate to be the temperature of different portions of the trip, we're estimating a single payload to have 18 watt hours per trip, and that is 4 hours of mission with a 1.2 safety factor. So that is ideally a lot more than we actually need. So over the entire HAB, that's going to be 108 watt hours just for thermal control. But again, that's made with very limited data, and is also inflated just in case. And so for the internal structure, there's not a lot to say there, but this is what that looks like. So this is the SS payload. So, but looking at the shelves, they are made in a modular design, so that way each payload can have different subsystems on different shelves, and they can just be loaded vertically into the wine coolers. And it's not pictured here because this sub team didn't need them, but there's also extenders. So say that the walls aren't tall enough for a particular experiment, then we can make them taller using extenders, which are just rings that are about the size of the base but hollow, so you can go up into them. But yeah, so this will be what every payload is going to be using as their internal structure, except maybe for payload 3. Regarding these 2 subsystems, are there any questions? Oops.
Where's the thermal heating pads being placed? How?
They'll be placed. Can you see my mouse on the screen?
Yes.
We don't have a final CAD model of it because we don't have the exact dimensions given, because each pad is different than, well, not completely, but slightly different than the others. So we plan to put them around these empty spaces vertically and kind of wrapping around the payloads. And so that way, like a completed payload, you'll have the internal shelving structure with the heating pads around it on 2 sides.
Is the power for these heating pads coming from inside of the CANSAT area, or is this like an external battery?
They'll all be within the CANSAT. And so the batteries that will be going to the thermal control as well as the thermal control's microcontroller will all be within the CANSAT.
Okay, and then you'll also have for each CANSAT?
Mm-hmm. That's right. Each CANSAT will have its own standalone system.
Okay. And I guess so you guys so I like how you guys came up with some numbers about how much power you're going to use. I mean, is 108 watt hours that we said, is that reasonable with the batteries you've you're gonna use or spec'd out?
Yeah, that is a quite frankly massive number. But
Watt
again,
hours, yeah.
the information that we have is I don't entirely trust the data sheets that we are given because they really are just literally 10 numbers. So that's just based on the information that they gave us. We will do more thermal control testing to really figure that out. This is very similar to a system that we used on our last tab. The only difference is that on that one, we just used nichrome wire. So we essentially made these mesh pads. In
Right.
this case, we're getting the mesh pads that are already made for this kind of experiment.
Good.
So I'm not expecting at all to get up to 108 watt hours even close, but given the information that we had from the data sheets, that is what that would suggest, but I'm not expecting that. We're also planning on using a PWM signal to more tightly control the temperature of the pads, but
Do you have some feedback coming in? Do you have you see a thermometer, right?
we have a thermal sensor.
Okay. Okay.
Yep, you have a thermal sensor. Is that directly feeding back into the heater as a feedback control, like Ryan was asking?
Yeah, it's checking, I want to say every 1.5 seconds, and it'll check the temperature. I believe we're going to have one. So we're going to be using a tangent function to get a nice average temperature based on what the heating pad will be putting out versus the ambient temperature. So every 1.5 seconds, it'll check what the temperature sensor is saying and then adjust the temperature outputting through the heating pads accordingly to keep the average temperature inside the payload at an ideal level.
Gotcha.
To answer your question, I'm sorry.
That answers my question. So I would make sure when you guys are doing this, you definitely need to evaluate your power because heating things just takes a lot of energy. Heating stuff just takes a lot. So verify your power, and then maybe it's good that you guys specified or identified that you want to keep above freezing temperature, right? Above 32 Fahrenheit.
Yeah.
I would just make sure then to not waste any electricity. Like make sure that it's maybe you have a range, like maybe there's a max temperature that it's just not on at all. Like maybe at 40 degrees Fahrenheit, if it's a temperature of a payload's above 40, then it just doesn't do anything. So you're not wasting electricity.
Absolutely. And different payloads obviously won't require so much at different temperatures. So for the mushrooms on payload 2 team, they obviously need to have a pretty high temperature relative to payload 3, which is just electronics. So different payloads can have a different temperature set, so it doesn't use that much power. This number was based on keeping a room temperature for all 6. Right. So that was a very high overestimate just to have a lot of wiggle room.
Good.
But yeah, because each payload can have its own system, they can all adjust accordingly for what that system requires too.
Okay.
So I'm going to jump back into Ryan's question. The image, the CAD drawing that you showed, are you actually showing the batteries for the heating in that CAD drawing?
No, this CAD drawing was made for the Special Subsystems team. This isn't actually the CAD model for the thermal control. I don't think we currently have one of those yet. Yeah. So the batteries that are pictured here are, again, for that payload. This doesn't picture the stuff for the thermal control.
Okay, so just make sure it all fits.
Yes, absolutely. Any other questions that we want to cover? Okay.
I think it's good. I like the heaters that you guys have found, and that everything's enclosed in that looks like capped on, some sort of capped on film. And just
can you repeat that question? I'm sorry.
I'm just saying it looks good. I like the heaters you found. That looks like they're the heating elements encased and capped on, which is that yellow film.
Yeah.
Just make sure that, right. Yep. Yeah. So make sure nothing's everything's insulated from the other payload, all the other electronics, so that nothing gets crossed but
Absolutely.
all right. I think my biggest concern is just having enough power. So you guys will just have to evaluate as you go.
Yep, absolutely. I agree.
I'm sorry. I think I missed it because I was trying to finish sending a message. Did you in the microcontroller that you're using? You have more than one? Is it one controller controlling all payloads temperature?
No.
Is it,
every payload will have its own controller.
Oh, okay. Never mind. All right. Thanks.
Yeah, for sure.
You're not taking up too much space from the rest of the payloads, are you? I guess.
No, so I have some here, but the microcontrollers are about an inch tall and maybe half an inch across. And then there are solid state relays to control the temperature for each heating pad. So the actual components is only 2 or 3 per system, and then those will all be on one. They'll all be soldered together in one board. What will take up the most room will be batteries.
Right.
But each payload will have its own space for batteries as is.
Is this gonna be a surface mount board that you guys are making?
I was planning on using perf board and soldering it all together.
Okay.
So.
That's fair. I guess I don't know what the Mega Pro Micro looks like.
I can actually show you one of these. It's just a really small microcontroller for it's not particularly powerful, but it doesn't really need to be. They're only about this large.
Oh, okay. Okay.
Yeah.
And they're through hole connections. Okay.
Mm-hmm.
Good.
Okay, great.
I have one recommendation if you're gonna do stuff on perf board. I don't know if we talked about it before, but doing stuff with a wire wrap and wire wrap tools for making your connections.
Wire wrap tools? Okay. I will.
Yeah,
thank you.
Write that down.
Yeah, I'm writing that right now. Thank you.
It's kind of an old-fashioned way they used to make space or really good connections for space hardware. They don't do it anymore, but it's pretty easy.
Okay, fair enough. Yeah, we will take that into consideration. Thank you. So if we're done with thermal control, I'm going to stop sharing my screen then.
Okay, and I know we didn't get to all of the AXP payloads, especially the full system, special systems payload, because there wasn't enough time. But the plan right now is for us to, at our AXP general meeting, record brief PDRs of those payloads, and then hopefully we can send it out to all you mentors at a later time.
That's good. That'd be a good thing to do. I guess if we're wrapping up, I guess for everybody here on these projects you guys are doing, this is just from my experience with doing stuff in AXP, is that electronics can end up being a bit harder than you anticipate. I would highly recommend you guys try to in advance. Like you guys, so everybody has testing and it's good, but make sure that when you do your testing or schedule your testing that you leave like time for you to make fixes and changes, for you to be able to fix things. And when you guys do stuff, if you guys do stuff on breadboards, it's usually where you start out is you have a breadboard and wire connections that are really they just kind of plug in. Those are great and a good way to get a good idea of how your whole thing connects together. But jumping from that to what your final like solder connection is actually kind of it's more work and more prone to problems than you might think. So I would do that sooner than later, and then do your testing or like your full mission sim testing with final soldered connected things, not breadboard. Breadboards are a good start, but when you guys do later testing, you should be doing it with your soldered connections, whether it's a proto board or whether it's some surface mount printed circuit board you're doing or however you're connecting. So that's my big advice is watch out on electrical. They can sneak up on you and bite you at the end. But I don't know what else you guys have planned, but I mean, you guys did a great job with your presentations here. I'm really impressed with everybody here and what they're doing. Like, I definitely wasn't doing this in middle school. Doing a lot, playing around, playing video games, getting in trouble, that kind of stuff. So,
Ryan, I
Good
thought you
one.
were a perfect poster child in middle school.
uh-huh. Right.
Justin's still on the line. He can say.
So many stories.
Uh-huh. So good work, guys. Really. I'm glad you guys are still doing this and still powering through with COVID in the way. So glad you guys can keep it going.
Absolutely. Thank you for your help.
Yeah.
Everyone that showed up to give us advice today. We all really appreciate it.
I wouldn't mind if you guys want to do more meetings, or it doesn't have to be a big PDR like this. It could be smaller things or more casual. So let us know.
Absolutely.
Thank you. We appreciate all our viewers for, we asked you to, some of you, we asked you to jump in for one, and then you find you keep getting sucked into more. With just about every volunteer activity, but we do appreciate you.
I mean, from my viewpoint, like I would happy for you guys to ask, and then me be able to, and then me try to do it. But if I can't do it, I'll let you guys know. But if you guys never ask me, then I definitely won't ever be there. So I prefer you guys ask me, and even if I shut it down or say I can't make it or do it, that's okay. Still, don't get discouraged. Keep asking.
Yeah, no, but thanks to Beth and Justin, and I don't know, all the, even if you guys can't stay for the whole thing, just the experience that you can bring in for the time that you can be here. And if you stay for the whole thing, thank you for giving us so much of your morning, and Beth getting up early.
Like these presentations you guys are doing, like doing PDRs, like this is what they do for real NASA projects. Like this is good experience, and being able to talk about it later if you guys are trying to get a job or internships and stuff like that. This is exactly what they do. Exactly what happens. So, and they always go overtime. even when they plan dead space for things to take longer, they're still overtime somehow.
Yeah, I think my PDRs can take like up to 1 to 2 days. I think 1 day is usually the standards that they carve out, like 8 hours.
Yeah.
Depending on like what it is, but it's
Not much stuff going on.
They're lengthy.
That's intense.
Yeah, and the students, you guys did great. I am so impressed. I mean, middle school or high school, what you guys are doing, you're setting yourselves way ahead on the curve.
I agree. I'll echo all of that. What's been said here. You guys have done a good job. When we ask a lot of questions, it means you guys are doing good. It's good that we're asking a lot of questions. When people get really silent and they just say, "Okay," that's bad. Usually.
Yeah.
So when we're asking a lot of questions, that's a good thing. So you guys are doing great.
Yeah, sometimes no questions means I don't even know where to begin. There's no hopes. Let's help you polish it.
I think it goes without saying too that for our launch on April 24th, all of you are of course invited to come. I think we've only got all the logistics yet, but we'd love to have you there.
Gotcha.
We're watching virtually.
Yeah.
Where is the actual launch?
The SAC Museum in Ashland, Nebraska.
Nice.
What time? At 10 a.m. you said.
Yeah, I'm not sure if we have a time of the day marked out yet, but it'll probably be somewhere around like 10 to noonish.
Sounds good. Yeah, I'm actually going to be back in the Omaha area that weekend, so.
Oh.
That works out well.
Great to see you.